Oh, I started it, Varun.
Yeah, cool. So, hey everyone, today we're going to be learning about a topic in machine learning called adversarial examples. And it's it's a pretty interesting area now that there's so many applications of ML. It's also important to look at where it can fail and where ML models can be tricked. And that's broadly what we're going to be looking at today. So yeah, this is generally the schedule that we're following in case you've forgotten. The membership portal code if you want. Okay, so let's go ahead and just get started. So what is an adversarial example, right? So like I mentioned, an adversarial example is basically something that tricks a machine learning model and makes it leads it to make a mistake. So what could this possibly mean? It could mean that, let's say you have an image classifier, right? And you feed a picture of a bottle. Usually it gets it right. The machine learning model tells you that this image is in fact a bottle. But if you had someone who was hell-bent on manipulating data and aims to trick your model, he could maybe feed your model a doctored image of a bottle, and suddenly it might just predict that it's, I don't know, a lion or something like that. And you must be wondering, oh, a line is quite different from a bottle. How exactly does that work? Wouldn't you be able to tell that someone had basically tricked your system? But the thing is, they would make the manipulated image look very, very similar to a regular image. And that's the beauty of it, I guess. It tricks your machine learning model, even though the input is not super different. Um, So this is an example of what some people do. So the original image on the left here would be classified as a panda with 57.7% confidence. And if you just add some cleverly chosen random noise, then your machine learning model will essentially predict that the image is of a gibbon. I'm not sure how to pronounce that, but anyway. And astonishingly, with like 99.3 confidence. So it's pretty sure that it's a completely wrong animal. So this is definitely something that you want to avoid. And you want to make sure that your machine learning systems don't are trained to avoid such problems, because this can lead to serious issues in many different situations. So you can trick a machine learning model in many ways. So the previous one was where we essentially just added some noise and it was classified incorrectly. You can also take the original image, rotate it a little bit, and that can also fool a machine learning model. Now, it's not immediately obvious why this happens, but it's just that if a machine learning model is not robust enough, it might not learn the true patterns of the data, and it essentially doesn't learn to classify some small variations of the original input correctly. So in this workshop, we'll talk about how you can create such attacks and also how you can defend from these attacks. So this is an example where you have a clean image that gets predicted as a washing machine. And after you apply some noise to the image, it predicts something completely else. It predicts that it's a loudspeaker. And even if you print out the corrupted image and take a picture of that again, it's still going to give you an incorrect classification. So there's definitely something going on here. And we should try to understand why exactly there are such problems. So does anyone want to take a stab at how attackers could use adversarial images, like what they could do with it? If they were able to trick a machine learning model, like what could they potentially do with it? Anyone?
For like a self-driving car, if you trick that something harmful is something harmless, then you can crash the car.
Yeah, that's actually my go-to example. Self-driving is where it's immediately obvious that there's a huge danger, right? If you somehow classify a pedestrian as an empty street, your car just runs over them. If people learn to manipulate stop signs as, I don't know, go signs or something, it can be quite problematic. And that's just one setting. Even in there can be a range of applications in which it could be potentially very dangerous. And especially now that you have so many security critical applications of ML, maybe in payments or even in tracking user data and so on, it gets more and more important to make sure that your model is not tricked by adversarial inputs. So, and actually yeah. So now we'll look at what kind of attacks you can do, right? So one way is that you basically adjust the testing images. So you just basically, once the model has already been trained, you try to provide it images doctored images that it won't do very well on. The other way you can attack models is by something called data poisoning, where if you have a machine learning model that's getting trained on large scale public data, maybe you could, for example, spam the data collection process with corrupted data, in which case the final predictions of that model would also not classify inputs correctly. The other way, exploratory, is what we'll be, in some sense, focusing on today, where you try to learn about what algorithm the machine learning model is using and try to exploit any patterns that you can from the model and create images that the model does not do well on. So these are broadly what kind of attacks you can use to essentially trick a machine learning model. And I guess one interesting thing that I found out recently is there was one incident where, like, I guess everyone knows that Google uses some sort of machine learning algorithms to predict how much traffic there is on a road at a certain point in time. And a bunch of users, and Google does this using the mobile phones of their users. So they see a lot of mobile phones on the street. They're going to predict there's a lot of traffic there. What a bunch of people decided to do is that they went to a completely abandoned street and just took a bunch of cell phones with them. And suddenly, even though the streets were empty, Google Maps basically predicted that that road was extremely busy and like predicted different optimal routes for other passengers. So that, I guess, would be an example of how you can sort of do an adversarial attack using data poisoning. Relatively harmless one, but I thought that was pretty interesting nevertheless. So yeah, I guess we went through quite a bit of information. Does anyone have any questions about what we've discussed so far? About like what adversarial attacks are? Any questions about that? Okay, anyway, if you guys have any questions during the workshop, like feel free to stop me right there and bring up whatever you've not completely understood. So let's go ahead and look at what types of attacks we have. So with one of the most important types of attacks is something called a white box attack, where what you essentially do is you assume, like, suppose you have access to a machine learning model as well as all its weights, right? And you have all the information of the model. And now using this, you try to figure out how you can manipulate one of the training set images and create an adversarial example. So this is where you assume that you have complete access to everything that the machine learning model has, and then try to figure out how to trick it. Now, this might seem like a silly thing to do because you almost never have complete access to someone else's machine learning model. But this is definitely a very good starting point. to figure out how exactly a machine learning model can be tricked. Moreover, you also sometimes have open source machine learning projects, and that information is available to everyone. So you want to make sure such projects are also resistant to attacks. So it's important to study how these attacks can happen in the first place. Uh, you also have black box attacks where you don't have access to everything in the model, but maybe you can feed the model an input and see what the output is. And you can keep feeding in different inputs and try to figure out what the worst possible output of the model is, and then repeatedly use such images to target the machine learning model. So there are a bunch of different situations over here, depending on what level of information access you have. And depending on that, you have a variety of black box attacks. We won't be going into everything in too much detail. We'll broadly cover one important white box and black box attack in today's workshop, which is sort of the foundational first attempt at machine learning attacks. And we'll see where we go from there. Right. Once again, does anyone have any questions or doubts or just concerns? Okay, if not, let's go ahead and look at the first way you can essentially trick a machine learning model, and that's something called projected gradient descent. And the idea over here is that normally when you're training a machine learning model, you look at your training data and you try to figure out which model weights give me the least value of the loss function. That's essentially the idea. Now, over here, what you want to do is try to figure out which input gives you the maximum loss in some sense. So I provide an image that I want to figure out which image the machine learning model is going to do worse on. So what I'm going to do is feed the image into the network, compute the loss, compute the gradient, and this time, instead of trying to reduce my loss, I'm going to try to increase my loss, because when you're making an attack, if the machine learning model does badly, that's good for the attacker. So that's essentially it. So you start from an existing training image, and then you use gradient descent to figure out how I can change the image so that the machine learning model does worse and worse. But there's one important difference between regular gradient descent and this. It's something called the projection step. And the importance of the projection step is that you want an input that looks you want a bad corrupted input that looks very similar to the original input, on which the machine learning model does worse. So you want to make sure that your corrupted image looks pretty similar to the original image. So you make sure that when you modify the image, you don't modify it by too much. Maybe you just mess around with a few pixels, or for every pixel, you don't change any pixel value by a very large amount. So in the end, when you first do a gradient descent update, and then you make sure that your update doesn't result in an image that looks very different from your original image. So I guess the main difference between projected gradient descent in adversarial attacks and with regular gradient descent is that in regular gradient descent, your model weights are variable. You keep training over and over again to find the optimal weights. In adversarial attacks, your model weights are fixed. You're trying to change an image and find the image that the model does the worst on. So it's kind of flipped. It's kind of the inverse situation, I guess. So yeah, that's basically what projected gradient descent is about. Once again, does anyone have any questions about projected gradient descent? Is there anything that you'd like a better explanation of?
So Varun, one
Yeah.
question that I'll propose is, so basically in gradient descent, the point is we calculate, some gradient buffer so we can update the weights, and those weights are the weights of our model. So as you mentioned, in this situation, the weights of our model are fixed. So when we calculate these quote unquote gradients with respect to the loss, what exactly are those gradients being used to update? Would they be, for example, RGB values of an image or something else?
Yeah. So basically, it's going to be the pixel values that you change. So you start off with one image that has maybe, say, D pixels, and you calculate the gradient of your loss with respect to that image, so the pixel values. And then with every update, you change the pixel values a little bit to figure out what image your model does the worst on. Yeah, so that's basically the crux of it. You calculate the gradient of the cost with respect to the input pixels of an image instead of the model weights. Yeah, so at each time you start off with an original uncorrupted image, and you keep using gradient descent to make that image worse and worse. So this is a scary looking equation that is a formulation of what exactly we're trying to achieve. So L of x comma theta is the original loss function of a neural network, right? So if theta could be the model weights and x is your training sample. So in the normal setting, you want to minimize the loss with respect to this, with respect to the image. But instead, in adversarial attacks, you want to, in some sense, find the image that maximizes the loss. So that's what this argmin refers to. You want to find the x. The x is the image where you have, say, D pixels normalized to 0, 1. So you want to find the image that minimizes g of x, which is equivalent to maximizing the loss, subject to the constraint that your corrupted image x should not be very far away from the original image. It should be within epsilon of the original image. So that's the broad idea. Find a corruption of the image that increases your loss as much as possible while not straying away too much from the original image. So I know that's a little bit to take in. So once again, if you have any confusions about what any of these terms mean, what the equation represents, feel free to stop me and ask. If not, let's go ahead. So let's look at what the algorithm is doing. And I'll keep going back and forth between these two slides to make sure that we've understood this correctly. So like I mentioned before, X is finally going to be a corrupted image. And we initialize that to the standard uncorrupted image. And then you compute the loss with respect to the input. So with respect to X. And then what you essentially do is you make sure in your update rule, you essentially update your corrupted image X by this term alpha into the gradient, where alpha is just some sort of learning rate. And you move delta away from the original image. Now, note that in traditional gradient descent, you would do something like the weights minus alpha into the gradient. Here, it's a positive sign. You do x is equal to x plus the gradient. And that's because you don't want to go down and find the minimum value of the loss. You want to find the x that maximizes the loss. So you go in the increasing direction of the gradient. So what that means is you take a step in the direction of the gradient and move upwards so that you find an image that is that the model does worse on. So we have a question in the chat that says, does this algorithm have a limit of how many pixels can be varied for each update? No, it does not. Every pixel value can be changed. The only constraint is that no pixel value can be changed by more than plus or minus epsilon. So you don't want your model to fluctuate. You don't want to find a corrupted image that doesn't look like the original image at all. It has to be subtle in some sense. So once you do that, once you add that slight corruption, that's delta to the image, you once again make sure that each component of X is between 0 and 1. And the reason we do this is that it's standard practice in machine learning to or in computer vision to ensure that your inputs are standardized. So if you have pixel values from 0 to 255, you kind of squash them in between 0 and 1. So this 0 and 1 actually represents like 0 to 255. So you'd make sure that even once you add the corruption delta, the resulting X is still a valid image. So it's still an image that you can see and visualize. And note that the reason that we clip delta to minus epsilon to epsilon is that we don't want the corrupted image to be more than epsilon away from the original image. So alpha is the learning rate, and typically we get optimal results with 10 updates for each image, and this is something that's called PGD10. So if you repeat this process 10 times for any image X, you're very likely to get an image that looks pretty similar, but the machine learning model does terribly on. So PGD10 is one of the strongest adversarial attacks that we have today. And in fact, most state-of-the-art results in adversarial attacks are some variations of projected gradient descent. And a good choice for the learning rate is epsilon by 10. Does anyone have any intuition on why this would be the case? It's completely fine if you're wrong. Just take a stab at it and make a guess. Okay, so it is a little tricky to understand why you would do something like this. But the idea is that in the end, you want your corrupted image to be at most epsilon away. So if you're going to take 10 steps to reach your corrupted image, roughly speaking, you'd want to step a distance of epsilon over 10 at every step. That's not exact, like you won't be moving exactly epsilon by 10 away at every update. But on an order of magnitude, that's roughly how much you want to be moving. And that's why typically if you repeat this process 10 times, a good learning rate is epsilon over 10. If you're going to repeat this process only 5 times, you might want to choose epsilon over 5. So that's probably that's probably how the PGD algorithm works. And this does give the best result, usually gives the best results that we know of today. So here's an example of what happens if you use PGD on an image. So the original machine learning model classifies this correctly as like a tabby cat with almost 90% confidence. But if you apply PGD on this image, make a few updates using the gradient with respect to the input and create an adversarial image, the cat gets classified as guacamole with almost 100% confidence. So it can significantly affect your results if your model is subject to such an attack, which is why these things are pretty extensively studied, right? If your machine learning model is classifying cats as guacamole, then you definitely do have a problem.
Varun, I have a
Yeah.
question. So why is it that if all the only thing we're actually doing in PGD is kind of maximize the loss, or maximize the loss, then how come in this example, right? How come it's so sure that it's guacamole? Like, why would it not instead like kind of defer to being like random? You know what I mean? So for example, why wouldn't it have like roughly equal confidence for each of the things?
Yeah, that's a pretty good question. And in fact, what I presented, like that you might actually have a situation where it's almost like equal confidence for all classes. That's because I gave you a very simplistic example of what g of x should be. But in fact, you could make g of x a different function, and you could also have like a targeted attack where you basically say, if I have an image of a cat, design g of x in such a way that it prioritizes classifying cats as guacamole. So I can even, depending on how I choose g of x, I can also have a targeted attack that can basically increase the probability of just one single class. We won't be going into that in too much detail, but it is something to look into following this workshop. There is a lot of work being done on how to get a model to change one class into precisely another class.
And I would imagine maybe this would be an easier task since it's more targeted, and maybe, for example, with the examples we were talking about at the beginning, where it's like the kinds of attacks you wanted to do, for example, on a self-driving car could be very targeted. Like specifically when it sees a stop sign, you might want it to do something else, right? So then maybe this would make it easier for attackers if they know they only have to trick the model when it sees a stop sign, then it can hit really hard at just trying to make the model misidentify the stop sign and not have to worry about anything else, right?
Yeah, that's a really good point. And in fact, you do have relatively simple choices of g of x that help you achieve that, which is why it's actually quite scary. So don't trust a Tesla with your life just yet. Um, okay, so while PGD does give us really good results, it does have some problems. And number one, it's computationally very expensive. And you have to compute the gradient with respect to each image 10 times. So going back, oh, my bad. Sorry. Yeah, so going back to the algorithm, this process of updating the x with delta requires computation of this gradient multiple times, and that's pretty expensive and takes a lot of computational resources. So it might be helpful to reduce the number of steps per image so that you can attack a model even with fewer computational resources. So the way you would do this is a sort of modification of projected gradient descent. And this method is called the fast gradient sine method. And it'll soon become obvious why that's the name. So here we do something that's very often done in computing tasks. We make an approximation. So we say that the loss function is approximately linear, very close to the original image x naught. This is basically a first order Taylor expansion. So you say that L of x naught plus delta is roughly L of x naught plus the derivative delta into, plus the input delta t into the gradient. So to maximize the loss, you basically need to make sure that this quantity, delta transpose into the gradient, is as large as possible. That's the goal, right? If you want to maximize your loss, you need to make sure that these two vectors are parallel. And you also are subject to the constraint that every entry in delta should not be more than epsilon or minus or less than minus epsilon, right? And it turns out that the solution to this is merely compute the gradient with respect to x once, and instead of instead of using the gradient explicitly, you simply take the sign of the gradient. So what does this mean? It means that if you have a vector like 5 comma minus 3 comma 2, it would just become 1 minus 1 1, and that's what sign of a vector means. So instead of looking at the actual values, you would just look at the sign of every component. And it takes a couple of minutes to understand why exactly that's the case, that if you want to maximize this term here, delta transpose into the gradient, then subject to this constraint of being within epsilon, then this is the optimal choice of delta. And this obviously has a significant advantage in that instead of computing the gradient 10 times and making 10 updates, we choose a delta that's approximately epsilon away from the original image. And we do that with just one gradient computation instead of 10. So this saves us a lot of computation time. Of course, the downside is that this method tends to be weak. This attack tends to be weaker than projected gradient descent, but it also saves you a lot of computing resources. Especially if you want to attack very large machine learning models, it might be better to try something like this as opposed to projected gradient descent, which can take forever to run. Personal experience, my projects in this class, even toy ones took like 10 hours to run for a single training run. So fast gradient Sine method does significantly speed up your training process.
So Varun, I have another question.
Yeah.
So when we normally, why is it that it takes such a long amount of time compared to something like just training a model normally, right? Like when we train a model normally, let's assume we're doing, full gradient descent, like no stochastic methods even. Like let's say we're computing over all of the examples, right, for each update. Then why is it that this is so much slower? It seems like even when we train a model, this doesn't seem any worse than just like the process we would have to go through when training a model normally, right? So why is it so important that we do these approximations?
Sure. So think back to like how you would train a neural network, right? You have your training examples, and then they go through several layers of weights and finally reach the outputs. And for each update, you compute the derivative with respect to each of the weights and then update it, right? Over here, when you have to calculate the gradient with respect to the input, I've not mentioned, it's not mentioned explicitly here for notational convenience, but this gradient with respect to the input actually depends on the derivatives of the weight matrices itself because of the chain rule. So all the derivatives with respect to the weights that you would do in standard training, you still need to do that and then compute the additional step with respect to the input. So you're already doing it, so it's already as expensive, except for you basically spend 10 times the amount of effort per training example because you make 10 updates per training example. So then it gets a lot more expensive. Fast gradient Sine method is order of magnitude roughly takes the same amount of time as standard training because it's just one update. But when you have 10 updates to make, it takes a lot more time.
Okay, so the problem is really that you're only doing all of this only produces for you one kind of corrupted image. And you typically would need like more than just one corrupted image, right? Because if we just want one corrupted image, we can just do the 10 updates and be okay with it, right? But if we want to make a lot of corrupted images for some reason, then we would have a problem, right?
Yeah, that's exactly right. And I mean, even if you want to target like cats, for example, you might want to target all the images that contain cats in it, not just one of them.
Right.
Um, so there's a question in the chat saying that so for PGD10, you need to backprop 10 times for each training sample. Yeah, that's pretty much right. So you would backprop 10 times for each training sample. And when you do that for all training samples, that's one epoch. So you would do it like for every epoch, you would update it 10 times, you would update each training sample 10 times. So it gets a lot more expensive. Okay, so moving ahead. Once again, the FGSM can produce pretty decent results. So this is predicted as a Macau. You using FGSM, you find some noise and you add it, and suddenly your machine learning model thinks that this bird is a bookcase. So FGSM can also produce strong attacks, not as strong as PGD10, but good enough in a lot of cases. So that's broadly two ways of attacking a machine learning model. And let's revisit something that we looked at in the beginning of the workshop, which is what's the difference between a white box and a black box attack, right? So the important thing is that if you know the machine learning architecture and the weights exactly, then all these gradient computations you can do that pretty easily, right? If you have access to all the model weights, the training data, and so on, this quantity can be calculated exactly using the chain rule, using backprop. But if you don't have access to the model architecture, the only thing you are able to do is maybe feed an input into the model and look at what the output is. In that case, it's you can't calculate the gradient explicitly. So what you might do is that at every single point, you try to estimate the gradient using several queries. So this basically means that if you have a very simple function, right, like just f of x, and you want to think about what the gradient of, or what the derivative of, let's say, sine x is, you may not know that it's cos x. But you do know that if you take, for example, sine of x plus 0.1 minus sine x over 0.1, that's going to give you a pretty good approximation of what the derivative is at sine x. And you don't actually need to compute the explicit derivative in this process. So you do something similar in the black box settings, where you estimate the gradient with respect to the input simply by feeding in, or simply by submitting some queries and looking at what the output is. So note that this is also helpful in the case that even if you know the model architecture, we've gone over how it's very expensive to do backprop so many times. So even if it's like a huge model, you're trying to attack, I don't know, GPT-3 or some or BERT, instead of explicitly calculating the gradients, it might be helpful to just look at the input-output pairs and use that to construct your adversarial examples, because it does not require nearly as much computational power. So even if you have access to the model information, it might be helpful to construct a black box attack. Any questions about what we've covered so far? Anything about the algorithms or the difference between white box and black box attacks?
So in this method where we approximate the gradient using the outputs, so doesn't this rely on our understanding that the inputs are kind of close to each other in space? Or am I misunderstanding this?
Yeah. So I mean, remember that the original goal is that you want to find a corrupted image that's pretty close to the original image. So you're interested in the gradients only in a small neighborhood. So if you choose like, so let's say you want to calculate the gradient at the image x, you just randomly sample a few small vectors and calculate the gradient at x plus h or x plus half h or something like that, and then use that information to figure out what the gradient should be.
Oh, so you're serving a few features within a single example. Is that what's happening?
Uh, Sorry, can you explain what you mean by serving a few features?
Serve so if you have an image, like you compute, you kind of look at the output for like a few of the um like pixels going in, or do you just look at the whole output? You know what I mean? Like what's the granularity that you're doing this surveying process? Are you kind of comparing different training examples, or are you comparing the features within a single training
Okay.
example?
You're doing it for every single training example. So in when you're estimating the gradient, you do it for each single training example. So what that would basically mean is that if you have a bunch of pixel values, like let's say X is some training example, maybe you vary each pixel by a little bit and look at what the output is for that. So just survey a few points next to your training image and do that for every single data point in your set.
Oh, so it's sort of like what we're doing in PGD, but it's like guess and check.
Yeah,
So like you kind of, yeah, okay. So you change it a little, you're like, okay, how did this do? And then you change it a little and like how did this do? Okay, I see.
yeah. It's it's not as random as it sounds, because if you sample enough points around your around each image, you can get a pretty reasonable estimation of what the gradient at that point is. And once you have an estimate for what the gradient is, it's the rest of the process is pretty much identical. Yeah. Any other questions about this? Okay. Let's go ahead. So this we won't be looking into in too much detail, but you also have, so in the previous cases, we varied every single pixel by a small amount. And in this sort of attack, you choose a training image and you pick any one pixel in that image, maybe change that one pixel's value by quite a lot. And it turns out your machine learning model will classify the image differently based on that. And that's very surprising, because in a pretty large image, even if you have a poor quality image that's only like 1,000 pixels, changing one single pixel value can change your model's prediction. So this is a case where your machine learning models are way too sensitive. And this is why it's important to make sure that when you're training your machine learning model, you make sure that it's resistant to all sorts of adversarial attacks. Yeah, so this is based on a technique called differential evolution. I'm personally not too familiar with it, but it definitely seems like an interesting method to research going forward. So yeah, even this can give pretty good results, especially if the image quality isn't too great when you only have a few pixels. Just one pixel can change the class of the image. So that's definitely something that's pretty cool.
So is this computationally maybe easier? Because like it seems, because one drawback I see of this is the human eye can definitely see this image has been like messed with in some way, right? But with our previous examples when we did PGD and stuff, at least I couldn't tell the difference between the corrupted image and the normal image. But here, obviously, as humans, we can see, okay, that pixel's off.
Yeah, that's a good point. So one of the problems with one pixel attacks is that humans can tell the difference. A computer might not be able to, so it's still a problem. But visually, you can tell the difference. And with PGD, you can't. In terms of computing, I'm honestly not sure which one is computationally more efficient. I think with the one pixel attacks, you might have to survey a bunch of different pixels before you find one that works. So that might again be pretty computationally intensive, because right off the bat, you don't know which pixel you should target ideally. So just searching for the right pixel might take a while. You might have to work on uh, like what was mentioned on the previous slide, where you might want to start with a series of candidates, change the pixel values in different places, and see which one produces the best attack. Um, okay, so we've spent this entire workshop being a little pessimistic, talking about how we can attack all the machine learning models that really smart people have worked on for cool applications. So now let's look at the other side and see how we can defend ourselves from these adversarial attacks. So the main way you would do this, or the most popular way today, is a process called adversarial training, uh, where you have your original training data, and instead of training on that data directly, the idea is that you start attacking your model in the training stage itself, so that when a future attacker attacks it, it's not as vulnerable to that attack anymore. You can think of this as sort of a vaccine. It's actually pretty much like that. Provide it with some attacks in the training stage itself, so that it does not get attacked later when the model is in production. Uh, yeah, and another method is something called defensive distillation, where what you do is you train one machine learning model on your training data. And your training data is typically labeled, right? Like 1 for a cat, 0 for a dog, or something like that. But your machine learning model's output is continuous. It provides a probability that the image is like of a dog or a cat. And what you do is that you use the training image and the output of the first machine learning model as your training data for a different machine learning model. So in this case, it's easier for the new machine learning model to learn from the data, because now it doesn't just have a class for every training example, it has a probability of every training example belonging in a particular class. So it instead learns a probability distribution, and this is relatively more robust to adversarial attacks. So we won't be going into defensive distillation too much in this workshop, but we will take a look at how exactly adversarial training is incorporated to make sure that a model is robust to attacks. So once again, scary looking equation, and we will break this down. So the optimization objective is framed in a sort of min-max way that can be confusing at first, but we're basically reversing the situation again. Here we're saying that I want to minimize my maximum loss. So what that essentially means is that during the training process, I'm telling my machine learning model, assume that a person is going to attack you and provide you with inputs that corrupt the original image by some delta. Now, the training process asks the machine learning model, what's the worst an attacker can do? And then it chooses weights theta such that the worst thing your attacker can do is minimized. So that's why you phrase it in a sort of min-max optimization problem way. You basically, so once again, to re-emphasize, you try to reduce the maximum amount of damage that an attacker can do. Note that if you ignore the minimum part of the optimization objective, just maximizing the loss for some delta, that is what an attacker would want to do, right? The attacker wants to maximize the loss. And so you, as someone who's deploying the machine learning model, will want to minimize the maximum damage an attacker can do. Once again, subject to the constraint that delta is not more than plus or minus epsilon for any pixel, because you know that an attacker is not going to try to trick you with wildly different inputs. He's going to try to corrupt your image in a very small way. So the idea of adversarial training is pretty intuitive. So normally you would compute, let's say you're doing something like stochastic gradient descent. You perform a gradient descent update for every training example and change the weights. Now, instead of using the training example, what you do is you do PGD, like projected gradient descent, or fast gradient sine method on that training example, find a bad image, and instead train on that bad image. And this time, you're making sure that the machine learning model knows that even the bad image has to belong to the original class. So in this way, when an attacker eventually tries to use projected gradient descent or FGSM, it won't be nearly as effective because your model is already aware that attackers might try to pull off something like this. So that's the key idea. Instead of using your original training data set, when you're doing your epochs, for every training example, find a corrupted image and train on that corrupted image instead. And this to date is the best defense against attacks like PGD and FGSM. Any questions about the adversarial training stage?
Yeah, so when you train on the when you're doing this training process, so you basically you first generate a bunch of corrupted image, and you're saying you train on the corrupted images. Do you all? I imagine you still keep the original images in the data set as well, or are those just removed?
Oh yeah, those are kept because you actually generate corrupted images for every epoch. So at every single
Okay.
epoch, you use the original training data to generate corrupted images. So your corrupted images are constantly changing. as they become stronger and stronger.
An event, okay. And I, so correct me if I'm wrong. Eventually, would you notice that the corrupted images become very similar to the normal images, or is that not the case? If your model is doing a good job.
Would your corrupted images become similar to the
Like would they basically converge to being exactly the same as the original image, or because if the whole point is you can't make this max, like you're trying to minimize the upper bound, right? That there can be an error. So let's say your model is doing a really good job of that, then that I would assume then the minimum of your loss and the maximum of your loss would be not as far apart that they would otherwise, right?
yeah, you're correct in that the loss would start closing down, so that if you classify it correctly, if you classify the original training point correctly, you'll also start classifying the adversarial image correctly. But it's more of a, it's, you can think of it as kind of smoothing the decision boundary, where uh, your original model, if your input varied a little, would make a wildly different prediction. But in this case, if the adversarial, the corrupted image would also be classified correctly, because your model has learned that slightly corrupted images should also be treated in the same way as the original image.
And just to clarify that point, it's I think Paymon may have gotten misconstrued with the idea of a generative adversarial model, where there's kind of a feedback, and we're trying to push our generative model to create image samples that are indistinguishable. But like Varun said, in this case, we're just trying to diffuse our decision boundary to include these perturbations within a particular class.
Yeah, yeah.
Yeah, and we have a workshop. Oh wait, no, we actually cut that out this time. But maybe next year when we teach A++, we will we'll have a generative adversarial network workshop. We have one, but we don't have time in the schedule this quarter to teach it.
Yeah, that should be quite interesting as well. Um, but anyway, coming back to this, even during the adversarial training stage, you have the same concerns with PGD. Projected gradient descent is during the adversarial training stage will make sure that your model is super robust. But of course, it takes a lot more time to train your model. With FGSM, your model will be relatively robust to adversarial attacks, but less so. So once again, there's a trade-off over here where FGSM is faster, but might not be the best defense. So in the training stage, actually, there's another interesting thing you can do to make your model robust to adversarial inputs. And in this method, you don't change the training process at all, and you don't have to retrain your model either. What you basically exploit is that you know that your machine learning model is not completely stupid, right? If it classifies a point correctly, it usually classifies nearby points also correctly. But our attacker tries to find that one point a little next to my original training image that that my machine learning model messes up. So what I can do to avoid this problem is, instead, when the user sends me an input to predict on, what I can do is I can sample images next to that point, make a prediction on each one of those points, and finally return whatever class was most frequently observed, right? So the idea behind this is that if my user gives me an adversarial input, I will sample other points next to the adversarial input, and those ones will be classified correctly. And so my final output will also be correct. So once again, this has the effect of smoothing your decision boundary, because your prediction remains relatively constant in a small neighborhood around any point. So this is one more way where you can smoothen your decision boundary and make sure that your model is robust to adversarial attacks. Okay. Cool. So what else is there in adversarial robustness? Honestly, we've just scratched the surface of what kind of attacks and defenses there are. researchers are constantly working on newer attacks and newer defenses. So, and there's a lot of work that's going into this. In fact, a lot of the research papers have been published in just the last 3 or 4 years. So it's definitely something that you all should look into. And there are also a lot of cool defenses that we didn't get to cover in this workshop, where you can in fact use non-differentiable activation functions that people just can't compute the gradient with respect to the input, and so adversarial attacks just fail. In this workshop, we focused on computer vision and how people can create distorted images, but the same is true in NLP tasks as well. So for example, if you ask a model what color is some object, it might correctly tell you blue. But instead, if you ask a slightly different version of the same question, which color is it, it might produce a completely meaningless output. So there are methods to attack and defend NLP models as well. So that's another interesting area to look into. And yeah, basically the takeaway is that there's a lot of cool work happening in adversarial robustness, and this is only going to become increasingly more important as you see ML deployed in pretty much every area. And adversarial robust models should be a priority so that we can be more certain that they're actually learning the important information from the data and they don't have any vulnerabilities. So yeah, that's pretty much all we had for this workshop. Justin, do you want to add anything?
Yeah, if there are no questions, then I think, yeah, nothing to add really.
Okay. I guess if we can look into a demo of how adversarial models actually work. So let's go ahead and look at this. The link to the code is available in the workshop slides, so you can always play around with this later on your own time. Okay. Wait, I think I lost my images. Oh wait, no, never mind. Cool. So here, I guess this is an image of a chicken, and this is a model that's been that's made to construct machine learning attacks. And one of the simplest attacks that we didn't actually go through in the workshop itself is that you can just add random noise to an image and see if it works. You might actually get lucky, and in some situations that might actually work. So for example, if you run this is an image of a hen. If you add some random noise to the image, it now thinks that it's no longer a hen, it's something called a lorikeet. I actually don't even know what a lorikeet is. But yeah, so that's something you can do with just random noise. You can also try FGSM. And here you can basically play around with the parameters. So you can make epsilon as large as you want or as small as you want. Here, if you make this 10, this corresponds to PGD 10. You might want to try something like PGD 5. Yeah, and you might also want to change which class that you're targeting. And yeah, this hen is now a safety pin, apparently. So feel free to play around with this code and to get a feel for what exactly it's doing. It's tricky to understand. If you want, the code is available like all the functions are also available for you to go through if you're familiar with PyTorch. Otherwise, you can just play around with this. That's pretty fun as well. And if you see, these look almost the same, but it classifies this as a snake with almost 100% confidence. So there's definitely a lot of cool stuff that you can do with adversarial examples. And this notebook also has links to further resources that you can use to learn more about adversarial robustness. And yeah, that's pretty much all we have in this workshop. So does anyone have any questions about anything? I guess not. So yeah, that's pretty much all we had. Thank you everyone for coming out to our workshop. I know it's midterm season, so everyone's pretty busy, but we really do appreciate you all taking the time to come to our workshops.
And again, if you guys do have any questions on this material or stuff on personal projects concerning AI, feel free to pop into our Discord with the message, or we have live office hours at 9 p.m. Pacific Standard Time on Thursdays. So feel free to check those out.
Yeah, and please fill out our feedback form. It does help us make our workshops better next time. If you felt like something was too fast or too slow, please let us know, and we try to improve our content. Thank you everyone for coming.
Thank you.